The modern data stack is a collection of tools and technologies used to collect, store, process, and analyze data at scale. But it comes with certain costs. Another novel approach to analytics embraces the newest hardware available, the NVMe solid state drives, which Ocient CEO Chris Gladwin says represent the greatest innovation since the dawn of computing, and thus begins hyperscale data warehousing. Find out more on this episode of Future Proof.
The future is here already. It's just not evenly distributed. Yet. Today's world teems with innovation. The nexus of hardware, software, and human ingenuity promises a revolution in possibilities. What does tomorrow look like? Witness Future Proof.
Yours truly, Eric Cavanaugh here with a couple real experts in the field, folks. We'll be talking to Chris Gladwin, who hails from my old stomping grounds in Lamont, Illinois, and Hyoun Park, who now hails from the West Coast, though he was formerly from Boston, Pactacan, Harvard, I believe, for a while
That's
there.
right.
That's right, boy.
Wicked awesome, Eric.
That's right, wicked awesome. That's right. Still got that toughness in him, right? Tough guys. A lot of tough guys in Boston. We're going to talk about a big topic, folks, the modern data stack versus hyperscale. So what does that mean? There's so much innovation going on in our industry these days. I credit open source with a lot of that. But as we'll talk about, hardware is always the foundation. I remember my partner, Dr. Robin Bloor, years ago, drew a stack, and he explained how all innovation in the computing world starts at the hardware level. And then it goes up to the OS and then the applications and so forth, all the way to the tip. But the foundation is the hardware, because the software can only do so much. And that's why you see appliances, by the way. So when you see the edge of the capacity of a certain hardware model, you'll start to see these appliances where they specifically design the software to run in the hardware. And that kind of hardware, that's been around for quite some time now. And that's happening once again at a company called Ocient. That's Chris Gladwin's third or fourth company, I think. He's a serial entrepreneur. Fourth, there you go. Really focused on. So they saw this coming, and they knew that it was going to be a big deal. And so they built around it. They spent years, hundreds, centuries of human hour time just banging away on rewriting drivers, rewriting all kinds of things to be able to take advantage of all this stuff. But we'll talk about what hyperscale data warehousing means compared to the modern data stack. And first, let's bring in Hyoun Park, maybe just to kind of comment on the modern data stack. And I've watched this, you've watched this with me together over the last 7 or 8 years or so. It really kind of started with the Hadoop movement when open source started climbing up the stack, and we did all this parallel processing and federated environments. There was a lot of hope in that day, and I think that it never fully paid off, but we learned a whole heck of a lot about distributed systems. And when you run distributed systems, you learn that there are all sorts of different problems and challenges you did not expect. And we've managed to tackle a lot of those. And I remember there was this whole, all these different HDFS versions. So you had like 6 or 7 at their peak, and then one dropped off, and another dropped off, and then 2 more dropped off, and it was down to 1. I think it's going to be kind of like that with these foundational models. Like they've got 18 of them now. They're all over the place. And you're going to see some winnowing and some optimization. But the modern data stack has scale out at multiple levels: data ingest, data processing, data storage. So you have these different component parts. And when I did some research on this, of course, the writing was saying, oh, it's easier. I don't think it's easier necessarily. It is more scalable. It is more versatile in that sense, because you got component parts that you can bring together as needed. They can scale out whatever you need. Is it the processing? Is it the ingest? They can scale out separately. That's a big deal. But what are your thoughts on the modern data stack, Hyoun, where it's going? And then just comment quickly on hyperscale data warehousing.
Yeah, so I remember starting my career back in the day when it was really easy. You just got your data, did your ETL job. Something popped in, you did your ETL back out to wherever it was going. Super simple. Easy work as a database administrator back in, call it the 2000s. And then, big data came along, and we got, orders of magnitude increases in what we were trying to support. And then everything fell apart. I think of the parable, kind of that story of the girl who did the Raja a favor, and in return, the Raja said, ask for anything you want. She said, give me 1 grain of rice. and then every day we're going to double this, right? So the next day she gets 2 grains of rice, then the next day she gets 4 grains of rice. And at first this seems extremely manageable. After 10 days, you've got 1,000 grains of rice. After 20 days, you've got 1,000,000 grains of rice. 30 days, you've got 1,000,000,000 grains of rice. And the story always goes about how that girl got so rich, and that's how the story ends. But there's another side to this. After 20 days, that 1,000,000 grains of rice, that's a 15-pound, bag of rice. Sure, you feel rich, you can feed yourself for, a month, fantastic. After 30 days, you've got 20 tons of rice. What the hell do you do with 20 tons of rice? You can't carry that back to your house. You need a herd of elephants just to drag that back to your house. At that point, you have broken the system. You don't have, call it in food terms, you don't know whether that's clean. You can't transport it. You can't turn it into anything. From a data quality perspective, we ran into the same issues with this modern data stack where you had to start working with data quality, data virtualization, data cataloging, transfer, being able to transformation, and then where does the data go? And with each of these pieces, we started developing all of these little niche technologies that filled those gaps, which is fantastic if you have an unlimited army of people to deal with these problems. So over the past decade, we created this, fantastically technologically interesting, I will say, stack of technologies that end up supporting all the capabilities that we used to be able to do in just a couple of tools 15 years ago. Now we have 10, 15, 20 tools to make sure that everything gets cleaned across structured, semi-structured, and unstructured data. And that's kind of where we're stuck now for the most part, because now we have, call it this hyperscale, where we're getting up to terabyte, petabyte, and beyond data. And now we need solutions to help us figure out what to do with this next generation, this next 1,000-fold increase in data, not just from a storage perspective, where I feel like we've actually kind of figured out how to do scale out storage, but everything else associated with that, it's a complete mess right now.
Yeah, that's a great story you told, by the way. I want to have you remember that one. It does a good job of explaining. I actually pulled that trick on my grandmother when I was like 5. I told her, give me a double a penny every day and I'll wash the dishes. She said, fine. I'm like, all right, Grandma, in 30 days, you're going to owe me a few million bucks. She's like, what? She thought that was a bit odd. But, I think you're exactly right. Now you have multiple parts. And again, it's very useful in terms of being able to scale out what you want to scale out. But make no mistake, now you have a whole bunch of interdependencies. You have a much greater complexity arena in terms of solving problems when something goes wrong. That gets a bit more challenging. And there are other interesting things going on. And the sun is flashing right on my eye. Look at that. It's kind of freaky. But let's bring in Chris Gladwin to comment on what he saw, because this modern data stack, again, is very compelling. For certain use cases, it makes a lot of sense. But the more component parts you add to a stack, the harder it's going to be to wrangle all that stuff together and to troubleshoot and to manage, it seems to me. I mean, some people really know what they're doing in that space, and it's fine with them. But what are your thoughts, and where did this hyperscale stuff come from?
Yeah, really, I'm gonna steal Hyoun's metaphor here, because I think the doubling the rice really is what has happened. Traditionally, in the data analysis, data analytics stack, you've had, CPU, DRAM, spinning disk. Those were your things, and they got bigger, faster, cheaper. But what's happened is, there was a $50 billion investment made by, semiconductor companies to bring a new building block, solid state, and a big part of that was the NVMe interface to make it standardized, and that has come to market. And today, those drives, each drive delivers 2,000 times the grains of rice per second, which is, at the end of the day, when you get down to the plumbing of how data is served and analyzed, it's in 4K blocks. That's what, when you ask if something, give me, read the data, you're going to get a 4K block. And literally, an NVMe solid state drive gives you 2,000 times as many. Well, like he was saying in the rice metaphor, well, now what do you do? If you're the database designer or the data warehouse designer, at the bottom of your stack, what you're used to is, a grain of rice every second. Now you get 2,000. and it's about to be 4,000. So you can't, it doesn't mean that magically you can just go that much faster. And we see this when you take an older architecture designed for spinning disk and you run it on solid state, it can handle about 10 times the speed. And then that's all you get. Because what's happening is there's a traffic jam at the grain, the rice processing center at the bottom of the stack. Like, I got 2,000 times, I can't carry all that. So what you ended up, which is what we did, is you have to now rewrite the whole IO layer. And the IO layer is the thing that like takes the rice and moves it to the right place. And, if you're, thousands of operations, 4K blocks, so 4,000 grains of rice, thousands of times a second, you can have a million parallel tasks in flight at every layer of the stack. So you have to rewrite the IO layer. That's 40% typically of the whole data stack. Jeez. Well, then the optimizer is the thing up above that designs how you're going to do the queries. Well, those have to understand what you can now do differently at the IO layer. Well, that's another 40% of your data warehouse stack. Next thing you know, you're rewriting allocators, you're doing it all in C++, and then you would be an Ocient employee, because that's what we did over the last 10 years. And I mean, that's exactly what we did, and that's exactly why. And the result is we really do see, because we knew what we were building for, like we can handle all the rice that the grandmother's got to produce. Mm-hmm. We will legitimately go 100 times faster, sometimes 10 times, sometimes 1,000 times, for these reasons, just because we designed for this.
Yeah, and the whole point of having analytical software is to be able to get the data you want into a place where you can run algorithms on it, crunch the numbers, figure it out. And you're solving for what is now happening, which is this deluge of data from lots of different sources. And you've got some stuff built into to kind of manage all that. So with the modern data stack, again, you've got multiple component parts that you stack up to do things, and they're all very good at their one little component part, but you do have these connections between them all. And, we've learned over many, many years, like even still today, if I put a hardwired cord in the back of my Big Mac here, it's going to be more stable than the Wi-Fi. It just is, because there's a solid connection there. So the less friction you get between component parts, the faster everything will go and the more seamless it'll be, right, Chris?
Yeah, what we're seeing now, because of those underlying capabilities and hardware changing so transformationally with solid state, is we're in the beginning of a complete transformation of the whole data stack, from using spinning disk and things designed for spinning disk for large scale, hyperscale data analysis, to where it all be solid state. This year, last year is the point where on a life cycle cost basis, solid state is crossing under spinning disk on a price per storage unit basis, because they're a little more expensive per terabyte right now, but they use less power, they fail less, they're smaller, things like that. So on a life cycle basis, it's crossing under right now. It'll soon cross under on just a pure terabyte basis. Like, that's a complete change in the industry, and everyone's going to switch over to solid state. You can see your phone has, your laptop has, your server will. There's just no doubt about it. It's going to happen. And that completely changes everything. And then starting around 2030, the next thing you're going to see is the cost per unit of performance. I was just talking about cost per unit of storage switching from solid state, from spinning disk to solid state. But now what's going to happen around 2030 is the cost per unit of performance on solid state will drop below DRAM. So that'll also switch over. And so we're in the midst of this, I don't know, it'll be like a 20-year shift, like a complete reset on how data is stored and analyzed.
That's interesting. I'm reminded, and Hyoun, I'll throw this over to you, of Hasso from SAP, and the vision he had like 20 odd years ago is very similar to what Chris is talking about. He realized, hey, at a certain point, the cost of memory is going to be equivalent to the cost of spinning disk. So why don't we build out our new version of SAP in memory only? Now, the one thing he did not predict, I would tend to think, is this thing called Kubernetes, which came along and really kind of upset the apple cart in that regard. But it's a similar vision of seeing where the hardware is going to take us and then designing around that and preparing for that. And I think that's a pretty big deal. What do you think, Hyoun?
Yeah, we definitely been trying to improve both analytics and data access over time with in-memory analytics, analytics on data, change data capture, all these things that were kind of designed to help us minimize the amount of data movement that was necessary. But at the same time, we always had these fundamental gates that kept things from going faster. So we just kept trying to find all these workarounds to be able to get around that and squeeze everything as small as possible to be able to get through the I/O. And there's a bit. Some of those were, fantastic for their time. Like I know SAP HANA. They get their, they have their critics, but a decade ago, it was a revolutionary idea. Did they fully capitalize on it? So. But the idea of doing software, in memory, and making that the core of the business was a great idea for the time, because it helped get around some of the fundamental challenges that hardware provided. But now we've gotten to the point where in-memory analytics is now more standard, and it's kind of a challenge of trying to figure out where to go next now that we have AI, which beyond all the hype is definitely going to accelerate the need for compute and create a whole mess of data. We know that much for sure.
Talking to Chris Gladwin of Ocient and Hyoun Park from Amalgam Insights. And Hyoun, you got some good questions for Chris to get into the weeds a little bit. Take it away.
Yeah, I was just curious. Chris, I do a lot of work with IT management, and although you solve a lot of problems around being able to deal with input and not having to deal with caching, being able to transform things in the moment. We're talking about massive orders and orders of magnitude, like several orders of magnitude increases in the potential challenges associated with metadata, with logs, with IT management and performance in general. And I'm curious how you think about managing that at that scale, especially as metadata and context became increasingly important for the business at large.
Yeah, what we're seeing, and we have the I guess opportunity and privilege to spend time talking with the organizations that are managing the largest data analyzing systems in the world. And it's great because it's just fascinating to see what they're doing. And really the biggest challenge they have is every new technology creates much more data than the old technology. If it's a telco and they're implementing 5G is amazing to customers. But one of the challenges it has to the IT professionals is it makes between 30 and 50 times the metadata that 4G made. And they don't get to say, well, I'll take 30 to 50 times the budget and I'll deal with that. So they get about the same amount of budget, and now they have to deal with it. And some of the things that, and that's true with car manufacturing and mobile phones and sensors and satellites, where the fundamental issue that most of these organizations are dealing with is just this immense increase in the volume of data they have to analyze, and they're already struggling with it. We recently did a survey of 500 IT leaders, really recently, past couple months, about like, what are your issues? And we just see it again and again in the results. People are talking about this scale, the data quality issues just become harder at scale. And really one of the biggest issues they have is it makes what they have to do to manage this kind of metadata at such a world record scale. It's hard, and there's no way around it that you need some talent. And the biggest issue they have is, 40% said the lack of talent available to analyze their data limits their ability to utilize the data. And that's a real problem. So those are the kinds of things we're seeing, is just this scale is creating, real challenges for these organizations, and they have to find a way to deal with it.
Yeah, just that challenge of parsing and understanding and linking and tracking information correctly at this massive scale is really, really difficult. I imagine that you have run into this issue as well, not just from a metadata perspective, but perhaps I'm curious what you've run into perhaps from a total cost of ownership perspective, simply dealing with this data at scale from a personnel perspective, or perhaps the value proposition that you're able to provide. You provide 500 times more input output. I guess you don't charge 500 times more than your competition as a result.
For sure. And one of the things we've seen, which I'm sure is not going to be a surprise to you and many of the people listening, is that data never starts out in the way you want it. I mean, it's always a mess. It's kind of a simple way of putting it. And when we decided to, build like the Ocient, build Ocient, which we knew was like building a fundamentally new stack for hyperscale data analytics, we didn't originally intend to also build a fundamentally new system for data transformation and loading. But it turned out that we just didn't see anything. Like, let's say you want to bring in, 10 terabits per second of a messy, million JSON documents a second. You're going to rip them apart. You're going to get them into relational schema. You're going to get them compressed, encrypted, indexed, secondary indexed, and showing up in queries at 10 terabits per second of flow within a few seconds, while you're running giant queries on the 10 terabits per second that have landed over the last month. Like that really is what we hear customers saying they want to do. So we ended up having, writing our own loading and transformation engine as well. And some of the characteristics that we needed to see in that one was, it needed to be lockless, in that if one loader does, terabit per second, then 500 loaders does 500 terabits a second or whatever it is. Like it needs to scale linearly. And that was, non-trivial. And we just hadn't seen anyone like say that's the problem I'm going to solve. So they had built things that were designed, for, smaller scale purposes. And then there's also the cost of that. Like it can't cost 500 times as much to load that much data. So we also designed that in such a way that, you could use, really cost effective servers. Our software, one core gets a lot done. And we charge by the core, and we charge by the core for all of our software, so that use cases where you're just hammering, loading, transforming, analyzing data like a lot all the time, it really becomes cost effective.
Yeah, I imagine like, although you've got these advantages, it's also kind of a challenge, because if I'm a data pro, I'm used to having all of these, call it stop signs, or all of these marts or caches that I'm used to having on the way to getting to the final product. How do you unlearn that?
Yeah. I mean, that is an issue. I mean, it is kind of like the rice thing again, like, oh, isn't it great that you have a ton of rice every hour? Well, what are you going to do with a ton of rice every hour? Because we essentially are delivering the rice. One of the interesting things that you see in disruptive technologies, and in a disruptive technology, I'm using the definition from the Innovator's Dilemma, the Clayton Christian book, is it is such a change. And you see these step function change, like broadband was one, the step function change in bandwidth to, homes and businesses. What it does is when you look back on something that is that transformational, 80% of the uses or so 10 years later are new uses that were only enabled by the change. And 20% is, what was happening, bigger, faster, cheaper. And one of the challenges with new uses is they don't exist. So the companies that will do these things, a lot of them don't exist yet, or the product lines or the capabilities that existing companies will now be able to take advantage, they don't exist yet. So one of the biggest challenges you have, a lot of people would think, oh, if you've got a data analysis platform that's literally 10 times the price performance, sometimes more, why isn't that you don't sell 1 billion next week? Because a lot of what people will use it for can't exist. So one example in my prior company, we did at CleverSafe, we did hyperscale data analysis, or data storage platforms as opposed to data analytics platforms here. And when you look back now on what are the things that software, and that software not only was successful on its own, but it became the way that everyone does, on large object storage. That was a new idea back then. But when you look at what people are physically using storage for now in that way, it's things that couldn't exist. So for example, cloud storage, where for either free or like $2 a month, you're storing terabytes. That can't exist if the cost is 100 times more. And we were one of the companies that helped reduce that cost during the 10 years we did that by about 100 times. And if it costs Apple or whomever is providing your storage $50 a month to sell it to you, they're not going to be able to do that. But if it costs 5 cents a month, all right, well, now it's a whole different ballgame. And so, photo sharing, just there's so many things that are only enabled once the transformation occurs, but they're actually really, really hard to implement when you're in the weeds because they don't exist yet. And that makes it
right.
tough.
And that object storage transformation, over the decade, over the past decade, has been incredible as well, because we went from being able to think about 100 kilobyte Word documents to 100 megabyte files, and using them the same way, from a practical perspective, copy and paste or moving things back and forth, wiping out the entire camera industry.
Yeah, no kidding. Chris, you talk about moving so much data so quickly. There's so many ways you can do things these days, so many different approaches with the modern data stack, for example. And think about streaming, like Kafka. Of course, there's also Pulsar. Then you've got Red Panda, who came along and basically looked at Kafka and said, we're going to rebuild that in C++. So it'll be a lot more faster, a lot efficient. How would you characterize what you're offering with hyperscale data warehousing versus what like a Red Panda or a Kafka is offering, a Confluent with streaming? What are the differences? What are the similarities?
Well, we're typically a consumer of those. Very often when you get into an implementation, you say like, what is feeding the Ocient software? It's very often a bunch of Kafka servers.
Really?
Or, that category of products. So that's where that data is going. So those are generally great products that, we've done a lot to complement.
That's interesting, because I remember the one challenge with the Kafka or with one of these streaming architectures is you got to have some place to put it. You got all this stuff coming in. Where are you going to land it? Just kind of like the rice problem. And so where you're going to land it is a tremendously parallelized system that can handle that I/O. Because to your point, and I remember talking to Foster Henshaw, this is like 17 years ago at a TDWI conference, and he was from Datopia. He was the CTO from Netezza way back when, and he came up with this whole architecture of that became the sort of standard. But he told me that back then, I/O is the hardest thing to deal with. It's the hardest thing to manage. Is it the case that the new observability we have into these systems helped allow you to be able to do that? Can you talk about where observability comes into this whole picture?
The thing that transformed it was what we were talking about earlier, which is solid state.
The hardware.
Yeah, I mean, DRAM can always solve the problem, but but DRAM is just crazy expensive, and that's fine if you've got gigabyte, a terabyte, but you have a petabyte, you have tens of petabytes. In some cases, you can pay for that much DRAM and the associated systems to make it all go fast, but usually you can't. And then the problem you had with spinning disk was you just didn't get the IOPS. The spinning disks, are a physical thing, in that the number of IOPS you get out of a spinning disk is a function of how fast the read-write head can move to a new track. The platter's got to spin around to the beginning of the track to start reading. That's been about 500, maybe 800 per second for decades. And so one of the interesting phenomenon you see in disks is it used to be when disks were smaller, you could read or write the entire disk in minutes. Now it takes days. So they're getting slower on a Moore's law adjusted basis because they just physically can't spin faster and the head can't, dwell in a track any quicker. And that's the problem.